Hello everyone, I am happy to invite you to this series of lectures on first level engineering thermodynamics course. The second level course is usually an applied thermodynamics course. This is the first level thermodynamics course, and the primary learning objectives in this course are to learn the first and the second laws of thermodynamics and their application to equipment and devices relevant to mechanical engineering. So, basically we are talking about equipments like compressor, turbine, pump, heat exchanger and so on. So, we will learn how to apply the first law to such devices, carry out an analysis and also use concepts from second law to evaluate certain things. So, at the end of the course, you should actually be able to carry out analysis of any device. So, given any device, you should be able to carry out an analysis of the device, a thermodynamic analysis of the device in terms of energy changes relating the heat interaction of the device with the work interaction of the device, and also calculate entropy changes of the working substance inside the device, and also calculate entropy changes or entropy generation in the universe as a result of the operation of the device. That is the learning outcome from this course. I have actually assumed very little in terms of prior knowledge, except to assume that all of you would have probably had an introduction to thermodynamics perhaps in your 12th grade in your physics course, and are familiar with the terms like pressure, temperature, volume, ideal gas and so on and so forth. We will anyway explore some of these things in greater detail as we go along. So, the outline of the course is as follows. We start with an introduction, and we discuss two important concepts in the in this module, which are the macroscopic approach and the continuum hypothesis. Thermodynamics can be learned or understood in using two different approaches. One is the so-called microscopic approach, which involves the kinetic theory of gases, and the second one is the macroscopic approach, and that is the approach that we are going to follow in engineering thermodynamics. Okay. So, we will sort of try to bring out what we mean by macroscopic approach and when it is applicable. Now, continuum hypothesis actually underlies the macroscopic approach. So, for the macroscopic approach to be valid, continuum must exist, and we will discuss what the continuum hypothesis is and under what conditions can we use the macroscopic approach and when we should abandon it and move on to a microscopic approach. In the second module, we discuss certain basic concepts such as system, control volume, property and state of a system, process undergone by a system, and we close the module with a discussion on temperature and its measurement. Okay. Now, these concepts system, control volume, property and state may are probably familiar to you, and they may seem somewhat simplistic. Okay, but what we will try to highlight during this course is that there are many subtle aspects involved with these concepts, and we will try to illustrate these subtleties through many examples. You may be familiar with them, but you are probably familiar with them in a somewhat superficial manner, and we will try to bring out subtle aspects of all these concepts through different examples. In particular, temperature and its measurement, we have note that we have sort of mention only temperature among the more familiar properties. We have pressure, we have temperature, we have volume, we have many other properties, but we have chosen to highlight temperature because temperature, although it seems familiar and is used quite widely in everyday use, it is an extremely subtle concept in thermodynamics, and we need to take a closer look at it. And we also look at the measurement of temperature. There are some fundamental issues related to measurement of temperature which we will highlight, and discuss temperature in that context. Okay. So that is why we have identified the temperature alone as a property to be discussed further, and not pressure, volume, and so on. Okay. Now, in the third module, we discuss work and heat. So, we first start with a thermodynamic definition of work. You are probably familiar with the definition of work in mechanics. Okay. It is basically force times distance moved by a particle in the direction of the applied force. In thermodynamics, this definition of work is not at all sufficient. It needs to be much broader than this. So, we will discuss the notion of work in thermodynamics, and we will also look at different forms of work and how to calculate different forms of work in practical applications. Okay. Then we move on to heat interaction or heat interaction of a system with the surroundings. So, we may be supplying heat to the system, or we supply heat to an engine, or we may be removing heat from a system like what we do in a refrigerator. So, insofar as heat is concerned, we do not really take a closer look at anything connected to it, except to say that either we supply or remove so much heat from the system to the system or from the system. So, basically in a given problem, you would either be given the amount of heat that is supplied to a system, or the amount of heat that is removed from the system, or you may be asked, given other quantities, you may be asked to calculate the heat interaction of the system with the surroundings. We do not really look at the heat in any more detail than that, in contrast to work. Work, we are we look at work in a much more detailed manner, but not so much for heat. Then in the next module, we move on to first law of thermodynamics for a system, where we connect the work and the heat to the change in property of a system. Okay. And this discussion will bring out the fact that a new property may be identified for a system, namely total energy of a system. Just like pressure, temperature, volume, and so on, the total energy of a system is also a property. Okay. So, that is what will come out of this module. In the next module, we look at a framework named pure substances. Okay. Basically, this module we have related the work interaction of a system, heat interaction of a system with the changes in properties of the system. So, we need to have a framework by which we can calculate changes in properties of a system. Okay. So, that is discussed in the fifth module. So, the type of working substances that we have in engineering thermodynamics, in particular mechanical engineering thermodynamics, are of two kinds. One is ideal gases. Note that a mixture of ideal gases may itself be treated as an ideal gas after taking care of the fact that it is composed of different components. So, we have ideal gases and we have two-phase mixtures in mechanical engineering. Under the category of two-phase mixture, we encounter the water steam working substance, which is used in many applications in mechanical engineering, like for instance the thermal power plant. And we also have two-phase mixtures of refrigerant in refrigeration applications. So, liquid refrigerant plus vapor mixture is also encountered as a working substance in refrigeration applications. So, these three substances cover almost all the working substances that you are likely to encounter in mechanical engineering, namely ideal gases and two-phase mixtures of water and water vapor, and two-phase mixture of liquid refrigerant and its vapor. So, now that we know how to calculate changes in property of a system, so we move on to first law analysis of systems, where we have for many different applications, we actually calculate work interaction given other changes in properties of the system and heat interaction, or any two or the three quantities being given, we try to calculate the third quantity, the two quantities being work, heat, and changes in properties of a system. So, we look at many examples in this module and try to apply first law to these examples and carry out an analysis. In the next module, we actually derive a form of thermodynamics for a control volume. This is actually not a different law from what we have already derived for a system. It is the same law, but applied to specific applications. So, the sort of applications that we have in mind are those where there is continuous inflow and outflow of mass, or inflow of mass but not outflow of mass, and so on. For instance, let us say that we have a compressor which takes in air, atmospheric air, compresses it to a certain pressure and then sends it out to a, let us say, a receiver or a tank. Okay. So, if we isolate the compressor, it is receiving a certain amount of air and absorbing a certain amount of power and sending out a same amount of air at a higher pressure. It may be running hot, so it also exchanges heat with the surroundings. So, for this type of a situation, we can actually simplify the form of first law that we derived for a system and directly apply it to this device. So, it is a very specialized form of the first law for a system. So, we identify a control volume, which is usually the device itself, as we will see later, and apply first law directly to this, so that given the power input and perhaps the heat loss to the surroundings, we can calculate the pressure with which the air will come out, or the pressure rise that can be accomplished by the compressor. So, such devices are called steady flow devices. Because it operates at a steady state, say 1 kg per second of air comes in, 1 kg of per second of air goes out, the device is warmed up, its temperature is no longer changing, it is operating at a constant temperature. So, such a device is called a steady flow device, and we will use a control volume for analyzing this device. Now, unsteady analysis is required when there is no steady inflow and outflow of mass. For instance, in this example, we said that the compressor compresses the air and then sends it to a reservoir. So, if I want to analyze the reservoir, carry out a thermodynamic analysis of the reservoir, note that the reservoir continuously receives air, but nothing leaves. So, it is operating in an unsteady state. So, we may want to know what the final pressure of the air will be after some time in the reservoir. So, this means that the pressure of the air in the reservoir keeps changing with time, and we want to determine what this pressure is. So, that calls for an unsteady analysis. Again, we will use the first law that we derived earlier, but apply it to a control volume, which is the reservoir itself, and carry out the analysis and obtain the quantities that are of interest. So, that would be an unsteady analysis. In the next module, we look at second law of thermodynamics. The first thing is we need to motivate why we need another law, what is deficient, or what is missing, or what is it that we cannot do with the first law is the first question that arises in our minds. Why do we need another law? Okay. So, that is discussed in the first in the initial part in this module. Then we define formally what heat engines are, both direct engines as well as reverse engines. Direct engines are ones produce power. Reverse engines are ones that absorb power but do something useful for you, like for instance a domestic refrigerator or an air conditioner and so on. Okay. And we define appropriate performance metrics for these devices, the direct ones and reverse ones. Then we look at a couple of different statements of second law, namely the Kelvin-Planck statement and the Clausius statement, and this naturally leads to the notion of reversible processes and the Carnot engine. As you probably know already, the Carnot engine is a power producing device which is composed entirely of reversible processes. So, we are naturally led to the reversible notion of a reversible process and the Carnot engine. And we then tie this up with the thermodynamic scale of temperature, where we look at or revisit some of the issues that we raised earlier with the temperature and its measurement, and then tie it up with the Carnot engine, and then define a scale which is independent of the working substance. Okay. So, we will deal with this in greater detail. The next module discusses entropy. So, just like the development of the first law led to the identification of a new property of a system, namely the total energy, the discussion of second law naturally leads to a definition of a new property of the system, which is entropy. Okay. So, we discuss Clausius inequality first, and this allows us to define entropy as a property of the system. Then we look at how to calculate entropy change of a system. Unlike microscopic thermodynamics, in macroscopic thermodynamics, we never actually evaluate entropy of a system. We only evaluate entropy changes of a system. Okay? It is very important to keep that in mind. In engineering thermodynamics, entropy itself is never calculated, only entropy changes are calculated. And there are a couple of different ways in which entropy change of a system may be evaluated. We will look at both those, either using TDS relations or given the heat interaction of a system, we can calculate entropy changes, entropy change of a system. The last topic of this module is the principle of increase of entropy, which is an extremely important universal principle. Okay, most of you are probably familiar with it already. The principle of increase of entropy states that the entropy of the universe remains a constant as a result of any thermodynamic process or increases with time. So, it remains a constant at best and usually increases with time. Any human endeavor generally results in this type of a change in the universe. The best endeavor leaves the entropy of the universe and changed, but most endeavors increase the entropy of the universe. So, that is called the principle of increase of entropy. We will explore this in greater detail. Okay. So, you may recall that this was one of the things that that was mentioned as a learning objective and also in the learning outcome. So, when you do thermodynamic analysis of a device, not only do you evaluate its work input or power output or change in property of the working substance or the efficiency, you are also expected to comment on how much the entropy of the universe changes as a result of operation of this device. That is a very important thing to calculate and also understand, so that you can try to minimize the entropy increase that the device contributes to the universe. Okay. The last module in the course deals with a special set of processes, namely cyclic processes. Here we look at two power producing cycles, namely Rankine cycle, which is nothing but the steam power plant, and the Brayton cycle, which is nothing but a gas turbine power plant. So, the Rankine cycle uses water as the working substance, water plus water vapor, and the Brayton cycle uses air as the working substance. Both of these are power producing cycles. The last topic is on vapor compression refrigeration cycle. As you know, the domestic refrigerator takes in electric power and maintains the refrigerator compartment at a low temperature. So, we discuss the vapor compression refrigeration cycle in detail in this last topic. We calculate the performance metric, coefficient of performance of the device, and we also look at any changes in entropy in the universe as a result of operation of the vapor compression refrigeration cycle. So, this is the broad outline of the topics that we will discuss in this course. I will be teaching primarily out of my textbook, which is Fundamentals of Engineering Thermodynamics. The second edition of the textbook is what I will be using. This is published by A&E Books India. But you are free to read from any textbook that you are comfortable with. It is not necessary that you should read only from this book. The material and the lectures are self-contained, so it should help you read any textbook or understand from any textbook of your liking. But the worked examples are all taken, worked examples, illustrations, and everything is taken from this particular textbook of mine.